AP Calculus students, how you doing today? Here's our first recorded notes. I have this on a big whiteboard at home, but most of you were with me last year, so you know that. I will be switching it up and getting you some notes some other ways. What we're doing is AP Calculus AB, that's APC abbreviated, 1.2 notes, analyzing limits graphically and numerically. First of all, you may be like, where's 1.1? 1.1 is just an overview of calculus, and we're going to look at that a little bit in a second. Again, as mentioned to you, limits are what you use in your everyday life. Our laws are limits that we have. Right now we have a lot of limits on what we can do and not do in the classroom for safety. And so we are just mathematically looking at limits. But this is something new that you've never seen before. So let's take a look at number one. Let's look at what the definition of a limit is. Now, when you look at number one here is the definition of a limit. Right here in the black circle. Notice this is exactly, I know what you're thinking. Yep, this is what calculus looks like. This is exactly what I was afraid of. We can do this. We can make sense of this. Be positive, stick with me, ask questions. So, the definition of a limit of a function f of x as x approaches c. So what we use to say as x approaches c is an arrow, right? Like you're approaching something, okay? So when we see this expression underneath LIM for limit, we say as x approaches c when we see it. So, and this f of x then is our function, and the limit equals a capital L. So let's just pull it all together. The definition of a limit is the limit as x approaches c of a function is equal to L. So let's look at each of these pieces. First of all, an input is x, right? We know that input is x, output is a function or a y value. So we are saying as x approaches some number, and that number, that value could be anywhere between negative infinity and infinity, that's its domain. So as x approaches some value, and you have a function, notice if you put an input into a function, you get an output of y, that equals the limit. So, in other words, if you are approaching x towards some actual value of x, and the y value or the function itself also heads towards a real value, then we do say that it has a value, the limit has a value, and that value exists. So, if as x approaches a value, your function also approaches a real value, we say the limit exists. If there is no value, if there is no limit as x approaches a value, then we say the limit does not exist. And we use DNE, does not exist, to say that. So this is so very important, is that x only approaches c. You are so used to, let's just look in red here real quick. You're so used to evaluating a function at an x value. A function at an x value. We are only approaching that x value, not actually landing on it. So x only approaches c. The limit as x approaches c is totally separate from what the value of the function is right at c. Now, why do we need limits? So I should say from the beginning, this video is going to be a little longer just because I want to take time. Not all the videos will be this long. Why do we need limits? What is this new thing we're looking at? On my little whiteboard here, let's go to section 1.1. You know your algebra and your pre-calculus. If we apply limits, and I'll explain what I mean, that turns it into calculus. The limits are the connection between what you know and what you're gonna learn. So what does that mean? That means on the left here, here's algebra. Find the slope between 2 points. You know how to do that, super easy. What if I tell you though, the limit is as the distance between the 2 points approaches 0. So let's say you have 2 points, you can find the slope. What if I make those 2 points closer together and closer together and closer together? So the limit, the distance of those 2 points is approaching 0. Wouldn't that almost be like finding the slope at 1 point instead of 2? And wouldn't that be really useful to know how fast, that would be slope, how fast something is changing at 1 point in time instead of 2? So limits is the connection. Here's another thing. Algebra, find the area under a curve by estimating using rectangles. Okay, so for instance, suppose you have this picture here. Here's a nice curve, and I put the black hash marks, and I want to know, hey, what's the area under that curve? Well, when you look at it, you're like, well, I don't actually have a geometric formula for that. So, you know what, let me draw some rectangles. Maybe I'll draw 3 rectangles that kind of match the curve, and because I know how to find the area of rectangles, and let me estimate that area. That's how you could use algebra to do that. Well, let's say this. Wouldn't it be true if you took your 3 rectangles and cut them into 6 and made the height match the curve a little bit more closely? Wouldn't that area be more exact? So what if I made 12 rectangles, 24 rectangles? In other words, what if I made my limit as the number of rectangles approaches infinity? What if I could put an infinite number of rectangles in there? Wouldn't I end up having the exact area under that curve? And that is calculus. We can find that exact area. Why would we need that? Because that could be the surface area of a real part that we make in manufacturing. If I gave it a depth, it would have volume, and that would be really important for us to know the material we need to make this part exactly. So limits is what connects our algebra to our calculus, and that's why we're studying it now. Just limits. We have to first understand so that we can move along. So let's move along. The first thing we're gonna do here, number 2, is we're going to analyze limits numerically using charts. So another reason this takes a little while is it takes a little bit to fill these charts in. So it's a little tedious, but very easy to do. So let's say I ask you for the limit as x approaches 2 of x squared minus 6 equals, and we're going to fill the limit in this blank right here. First of all, in your mind, picture x squared minus 6. You know what it looks like. It's a quadratic, it's a parabola that goes upward, but it's been pushed down 6. So you can picture that in your head. But let's do this. Here's our function, x squared minus 6, right here. And what we're gonna do is actually make our x approach 2, right? Here's 2 in the middle. Now there's 2 ways for us to approach an x value of 2. X's are horizontal, they're on the x-axis. So how do I approach x? Well, I approach x from the left, or I approach from the right. So notice that's what we're doing right here. Here's 2, okay? On the left of 2, 1/1000th of a way is 1.999. A little bit farther on the left from 2, 1/100th of a way is 1.99. And then 1/10 away is 1.9. So notice if I put these x's into the function and get its y value out and write them right here, that will give me a value of the function as I approach 2 from the left. Now let's approach 2 from the right. A value really close to 2, but on the right of it, 2.001, 1/1000th. little farther away, 2.01, 1/100th to the right of 2, and 2.1 would be 1/10 from 2 on the right. So notice that I can approach 2 from the right. And notice our standard is we get really close to 2. We get 1,000th away. Okay, so how do I write that? How do I write that I'm going to approach, x approaches 2 from the left? What we do is x approaches 2, and in the exponent position, we put a negative if we're approaching from the left because our negative numbers are on the left. How do we say that we are going to approach 2 from the right? X approaches 2 from the right. We put a little plus sign in that exponent position, saying that because our positive numbers are on the right, that we're approaching 2 from the right. Of course, we would never put these symbols here and here on the left-hand side of 2 because now it looks like a -2. Now it looks like a +2. So when I am looking for the limit as x approaches 2, I have to evaluate it from the left and the right. So let's go ahead and do this. So we're going to put these x's into the function and output a y value, and to the thousandths place. That is our objective in the standard that we stick with in calculus. So what's the easy way of doing this tedious problem? Let's look at the calculator. So we're going to come on down here, and rather than keep typing x² - 6 into the screen here, let's go to a y equals, and let's do x² - 6. And let's just go ahead and do a zoom 6. All right, we knew what that looked like. There it was. Now, to fill in these values here, our table isn't useful unless you put your table into 1/1000ths. So let's use the graph. Let's come on back down to the calculator. And what I am going to do is I am going to use, instead of the trace button, second trace. So second calc. And notice number 1 is value. And when you hit that, it says, hey, what x do you want to go to? Well, I want to go to 1.9 on my chart. So when you type that in, 1.9, there we go. It gives me the value of the function where x is 1.9, -2.39. Let's fill that in. My marker got a little dry because I kept it open. There we go. Let's go to an x value of 1.99. Again, on my calculator, when you look down here, I'm going to do second trace. I'm going to hit value, and now I'm going to put in 1.99. And it gives me my y value, -2.0399. There we go. And I'm going to do that again. Little tedious, but isn't it nice to know it's easy? There we go, 2.004. Okay, when we put in a 2, I could use my calculator, but I can see what that value is. Oh, that was a negative, right? That 2 squared is 4, -6 is a -2, right? Don't need the calculator for that. Let's ask for a value of 2.001. Second calc and value, 2.001, -1.996. Okay, 2.01, -1.95, -1.960. Notice I'm always going to the third place. And 2.1 is our last one on this chart. Go, -1.59. There we go. All right, so let's take a look at it. Let's approach 2 from the right and from the left. The values to me seem to be getting closer to a -2 as I approach from the left and the right. Take a look at these y values. Hopefully you agree with me, they're approaching a -2. And so that is the limit. Now, does it happen to where x is 2 also hit -2? It sure does. Does that happen all the time? Let's find out. Let's do the limit is, this is b. The limit as x approaches -1 of this quadratic divided by that linear function. Okay, and let's take a look again. Notice we're approaching -1 from the left, and from the right, we get 1,000th away. Please put this in your calculator very carefully with the parentheses that I have. That's going to take me just a second to get that right. Okay, x squared minus 3x minus 4. And divided by, and I'm going to put x plus 1. All right, again, a zoom 6, and let's get those values. On my calculator, which we don't need to look at, after this, because we'll know what we're doing. Second calc and value, and what was I shooting for? At -1.1, and the value of the function is -5.1. -1.01. -5.01. -1.001. -5.001. Just taking a look at the pattern, seems to be approaching a -5. Let's put in the -1 so we don't have to do extra work. Oh, it doesn't give me a y value. Let's take, do you mind putting on the, there's no y value there for a -1. Why does this make sense? Let's take a look at the function up here. Well, what if I put in a -1 here, here, and, oh, okay, right here. When I put a -1 into the denominator, I get -1 plus 1 is 0, and I can't divide by 0. Okay, well, I'm just going to say that the value of the function at -1 doesn't exist, right? There's nothing there. Let's do these three values. -4.999. All right, let's take a look at the limit. Let's approach x of a -1 from the left and the right. Let's take a look at those function values. As you approach x, an x of -1 from the left and the right, you can see that the value of the function is approaching -5. Notice in this case, though, the value of the function at -1 doesn't exist. Notice that these two are different, okay? Again, over to the purple here, so very important. X only approaches C. The limit as x approaches C is a totally separate issue from the value of the function at that C. Notice that it's different. Sometimes it's the same, it can be different. Let's take a look at C. The limit as x approaches 5 of 3 over x minus 5. You know, I should really have some parentheses right there. I'm going to add those. Going to put that in my calculator. And you know what I'm doing. You could almost like zoom 6, you could skip over this, but I have to fill it in so that you can see what I'm doing. I put this in my calculator, I'm putting in these x values, and I'm filling in my chart. So 4.9, the value of the function is a -30. Whoa, -300. $4.999, -3,000. Wow. Take a look there. As x approaches 5 from the left, take a look at that. This is -30, -300, -3,000. I'm not so sure that it's approaching, the function is approaching any value. Let's take a look. When we put a 5 in here, because it's super easy, notice we can't divide by 0 again, so this does not exist. Let's do these x's. 3,000. There we go. 300. And you would see if you put 5.1 in your calculator, you're gonna get the 30 again, because now it's just the x is at negative. So take a look as you approach, x approaches 5 from the right. As you approach 5 from the right, notice these values, with these y values, are not heading towards any particular value. These from the right, these function values are getting very large. These values, when you approach from the left, approach 5 from the left, are getting very, very small. This means that the limit does not exist. Notice in this case, the limit doesn't exist, and neither does the value of the function at 5. They happen to match. Of course, we need some trig in there. Trig is the rule, not the exception. Be really careful. First of all, make sure you're in radian mode and use the parentheses just like you see here. Okay, and then we're going to evaluate the limit as x approaches 0. I think this one is kind of cool. So I'm going to check my mode. I am in radian mode.
Hey, buddy.
Squirrel at the window. Oh, he needs peanuts.
He's going to have to wait.
He is going to have to wait. We feed our squirrels peanuts. Okay, let's clear that out. Okay, so let's see. I'm going to do sine.
While we're waiting on that, he wants to talk. Come on. You want to scratch on the window? Okay.
Boy, I'm getting slower as time goes by here. That's okay. We're almost done with the tedious part. Okay, I have it in my calculator, this function here. Now, in this case, I am going to hit, if you don't mind bringing the phone here, zoom, and I am going to hit 7 instead of 6, just because it's trig, and we have sine. So I'm going to hit 7. If you hit zoom 6, you would be just fine also, but I've got trig going on, so I'm going to use it. So notice that we're going to do the limit as x approaches 0. Now, let's just take a quick look, if you don't mind bringing that phone down here again. Let's look on my graph. I know where x equals 0 is. It's right here. So if I approach from the left and the right using my fingers, and I take a look at the y value, it seems to be about 1. Let's see if that actually happens when we fill in the chart. Here we go again. I'm going to do second calc. I'm going to do a value of a negative 0.1. That is 0.993. A value of negative 0.01, 0.999. Actually, it's 0.9999. I'm going to go a little further. There we go. And notice that's very close to 1. And a negative 0.001. I forgot the negative. Oh, wow. It's 0.999. And on and on and on.